lecture to finish off Chapter 17. The topic that we're going to cover today is eccentric impact. So we are back to the idea of momentum and impulse, or momentum in the normal and tangential direction. So when we start talking about this topic, section 17.3, you will also see that there are a lot of direct analogies to our previous discussion of momentum, especially when we talk about that impact that does not occur with the objects coming toward each other from the line of impact. So we have some other directions. So here we have our two potato chips, and what we see is that the end direction, just like before, is the line of impact, and the t direction would be perpendicular to that direction. In this case, we have a velocity of A and a velocity of B that are not directed along the axis N. And so what we're really looking at is what is going on before and after, and then during the impact. So if you remember, while the two objects are in contact with each other, there is a period of deformation where there's an internal impulsive force that depends upon the force of contact between the two, or the vector r. So we have r dt, the integral of r dt, which is the impulse during that period of deformation. And then as the two objects separate, we have a period of restitution, and the impulse there is equal to some other force, p dt. So the principle of impulse and momentum tells us that the coefficient of restitution is the ratio of those two impulses. Or in other words, how quickly or how well the objects resume their normal shape depends on the ratio of those two impulses. So in addition to the coefficient of restitution being equal to that, the coefficient of restitution can also be thought of as the ratio of the difference between the outgoing and incoming velocities. Or actually, this is written, they are velocities in the sense that we have a very strict definition of the direction, which these are all, when we talk about coefficient of restitution, these are the components of the velocities in the normal direction. But because it's defined with that subscript n, we write it as though it's a scalar. So it's really, it is the component in the normal direction. So the primes, just like in our previous discussion of impulse and momentum, VB prime and VA prime in the normal direction refer to those velocities after the impact. After the impact has occurred and the bodies are moving with whatever speed and velocity they are afterward. And then VAN without the primes and VBN without the primes are prior to the impact. So on the top, you notice when we're talking about the velocities after impact, it's the velocity of one minus the other, but the objects are reversed in the second. So in other words, if this is B minus A after impact, it's A minus B before impact, just to get the coefficients straight. All right, so that actually is the entirety of the lecture for the eccentric impact, but we have a few example problems. I'll work through at least two of them with you so that you can see what this looks like. So anyway, here we have a 0.05 pound bullet, and it's fired into the side of a square panel, which is initially at rest. And I always look at this problem, I think if there's no depth to that square panel, it's kind of an odd problem because you're going to have to be a pretty good shot to intersect it, but that's not really true. That's not part of the problem. Determine the angular velocity of the panel. So we want that omega value. Immediately after the bullet becomes embedded, the impulsive reaction at A, up here, in other words, up in that pivot, and we are assuming that the bullet becomes embedded in 6 times 10 to the minus 4th seconds. All right, so the strategy for solving this problem is to consider the system to be the bullet in the panel, and to apply the principle of impulse and momentum. The second would be that the final angular velocity is found from the moments of the momenta and the impulses about A. So in other words, we're going to use eccentric impact to find some of the stuff, and then we're going to have to go back and dig into the idea about moments of momenta again, as we've done earlier in this chapter. And the reaction at A, which we're talking about forces and possibly moments, is found from the horizontal and the vertical momenta and impulses. All right, so you can think about this. The setup is going to be drawn very similarly to how we've drawn these types of things in the past. We have a before condition, and we have something going on with the rotation of that plate, the reactions at A that produce that rotation. And so we have the inertia vector, or excuse me, it's not really the inertia vector, pardon me. The mass times velocity, in other words, the linear momentum of the mass center. And we also have the rotational component, the I bar omega, about the mass center. So this is eccentric because the pivot point A is not located at the same point as the mass center G. So we take the system momenta plus the external impulses. The word escaped me for a moment. And that will equal the system momenta at the time too. So this is exactly the same sort of a setup, except for now we have this rotational piece as well as the linear piece. So some of the equations we can use, we solve for the moments about A, where we have a momentum times a distance is equal to the momentum of the mass center times the distance plus that rotational piece, or the I bar omega. So we can separate some things out, come up with an idea for what omega is based on the solving of that equation. And we get a rotation of 4.67 radians per second in the counterclockwise direction, which makes perfect sense because if the bullet hits the plate, you're going to expect the rotation to be counterclockwise. If it came out to be clockwise, there'd be something wrong with your math. So there you go. And then continuing with that idea, we then instead of breaking it down into the rotational stuff, when we're solving for those reactions at point A, we break it down into X and Y directions. And when we do that, we are also able to find out what those reactions are. It's kind of surprising to me. Not that, well, it's kind of surprising to me that that A sub Y component is equal to 0. I don't really know how realistic that is. But that's definitely, with the conditions in this problem, that is true. We're not really taking into account the weight of that plate. All right, here's another one where we have an eccentric condition. We have a ball hitting a bar or a rod. The rod is pivoted at point A at the top, and the mass center is at G. And we have this ball hitting the rod below G. So if we're hinged at A, we know that's where the pivot is going to occur, and we want to determine the angular velocity of the rod and the velocity of the sphere immediately after impact. All right, so when we go through the problem set, we set it up exactly the same way. We take moments about A. We need to include the momentum, the moment of the momentum about the mass center, which is this term, and the I bar omega prime, which is the rotational piece. And going through that, we can't solve directly for either omega or velocity, so we need some more equations. At that point, we're going to take those moments about A, and we have something about the relative velocities, and at that point we have two equations into unknowns, so we can solve for both omega and v sub s after we do that. But the point of this, the setup is exactly the same. What drops out is, the order in which things drop out is different mathematically, but the setup is exactly the same. All right, and then the last problem that we're going to cover in Chapter 17 is a conveyor belt problem where we have a square package that has a mass m, and it's moving down. So we're moving from the right to the left. and it moves with a constant velocity. At the end of the conveyor, the corner strikes this rigid support. The impact is perfectly plastic. And you remember there's plastic and elastic collisions. We've talked about that. That tells you something about the coefficient of restitution. So we're going to derive an expression for the minimum velocity of the conveyor belt for which the package will rotate about B and reach the conveyor belt C. So basically what it's saying, if it doesn't come down fast enough, it's just going to get stuck there till package next comes up and knocks it out of its place. All right. So once again, same setup. That's a broken record. That's the run home to, this is the good comforting part. It always works the same way. System momenta plus the external impulses equals the system momenta. All right, so we take moments here about point B. We come up with a relationship between the velocity of the mass center of the package and omega. And then the next thing we want to do is to see what is the minimum, essentially, value of the velocity that's going to tumble it over. So we take a look at the principle of the conservation of energy, and we determine that minimum initial that will move it toward B. So we go ahead and we set that up. The T2 then has to have some component of omega is really what we're talking about. So we have an expression then for what that omega has to be, and then we can solve for what the velocity has to be. So this value, the velocity being equal to 0.712 times the square root of the gravitational acceleration times a, which is the distance here, which makes sense as well. That is the minimum that is going to be required. If it goes faster than that, it will tip over and fall onto the horizontal conveyor belt. And if it doesn't, it will stay forever suspended until something knocks it off of its pivot. All right. So that's it for chapter 17. Do you guys have any questions yet, or do you think you're going to be need to get into the problems a little bit before you start having questions? Right. The thing I would mention to you, just in terms of solution, when you look at solving the problems, start with this equation. That will always get you where you need to go with these. And if you stay, then you have these other ideas where you can work. You have that rotational piece that when we worked with momentum before, we were not talking about that. But we are going to have not only the normal and tangential stuff, but we are also going to be able to put things into X and Y components. And then if we use energy, of course, we don't have to really think about direction at all. We just think about the amounts. All right. So that's it for chapter 17. I am going to post the lecture, including the last lecture. I'll post 2 more homework problems. So you're going to have a total of 6 homework problems in total for chapter 17. And then we will continue next time, which is a while from now, with chapter 18, and that will finish our discussion of dynamics for the year. All right, well, everybody have a great day, and we will talk to you all real soon. There we go.